Okay, we're going to do our little online class today. I have a short lecture to go over, and then there's some videos to watch that kind of relate to these. There's a couple examples and some videos of some more theory and things like that that might help you understand a little bit about vibration. So, we talked last class about vibration a little bit. We kind of started introducing it. We talked about some different types of vibration, and we looked at some examples of different types of motion. We're going to continue on with that today. So we talked about the different types of bodies. We looked at rigid bodies, structural bodies, and mechanical bodies, and we're going to focus a lot on sometimes rigid bodies, but mostly the structural bodies that have some type of flexibility in them, and how they might relate into some of the mechanical systems, and especially with rotating machinery that we have. Some things that we're going to be looking at is that we can have a force applied on the body that would cause it to move, that's causing the vibration potentially. We could also have forces due to the elasticity of the body, so as it bends, just like a spring has a force that it generates. We can also have forces in any types of flexible body that as it bends or twists or stretches, that we can look at a force there. And then there's also forces due to the dynamics, the mass times acceleration components. Those are sometimes considered to be inertial forces. So we'll be looking at those, and we're going to look at two different forms, forced vibration forms, where you have the forcing function of the applied load included, and then we also have free vibration, where it's initially loaded, but then the motion is just due to the vibration of the system without load. Some common forms of vibration that we see around us, some things that you maybe learned about before with music, sound. We can look at wind and boats on the sea and things like that. We're going to focus on the ones that are more involved in engines and machine parts. And we mentioned last time too a little bit about that the vibration is necessary, but it's when you get high magnitudes is when there's issues. So that lead to instabilities, and there's other side effects too that we can try to avoid. But sometimes we want vibrations. I have a couple videos for you to watch on sorters and compactors to show you what that might look like. If we write out our equation of motion, I'm going to show you how we get this, but we get a second order differential equation, which looks like at the top here, the mass times acceleration plus the load of the spring is equal to the forcing function. And this second order differential equation has a couple different solutions. The one is the particular solution, which is based on the forcing function. We'll look at forced vibration a bit later, so we'll look at those forms later on. Another form is the general solution, which there are two possibilities. One where there is no motion at all, which is the trivial motion where x is equal to 0. That's not the one we're looking for. We're looking for the one with free vibration where x is not equal to 0. And it's typically some type of sine or cosine combination of terms where the natural frequency is found from k over m. The form that we could also write it in looks like this, where it's some magnitude times e to the st power, and s could be some imaginary number times omega. That's kind of the general form, which when you write that out, it actually is a cosine-sine combination with an imaginary component. There's other equivalent forms that could swap the sine and cosine potentially, I think, but we're looking at harmonic motion, and with the exponential term in there, we can get some dampening to occur. We can describe that in this form also. But all of these need some type of initial force to cause it to move. Could be a displacement or a velocity also, but to get that motion going. So we mentioned damping, And we're going to come back to that a little bit later, but just to define what it is at this point, the top left graph shows an undamped vibration, so you see the oscillations continue on at their same amplitude. The one in the middle shows a damped free vibration, where you see the oscillations get smaller and smaller as time goes on due to the damping, and you can compare the two. The period should remain the same, roughly, but you can see that the oscillations dampen out. We can also have some conditions where we have an initial position and an initial velocity, which may start the graph off a little bit differently, kind of like a phase shift. The solution form, you can include that in there. But we'll look at those a little bit later on, but we will be referring to the initial position velocity, though. So all systems will have dampening in them at some level. Otherwise, you'd have a perpetual motion machine, which doesn't exist. So usually it could be within a material, just the friction internally as the body is being flexed in different directions, that there's this energy loss. It could be generating heat in some way due to the friction, but there's some type of energy loss in the system which causes it to dampen out. Some systems dampen out quicker than others, and we'll be looking at some springs that take a long time to dampen out, and in other situations they'll dampen out quickly. So the different types of dampening that can be examined, we're going to be looking at proportional dampening, which basically describes that the amount that it dampens each cycle is proportional to the next dampening cycle. So we'll get back to that a little bit later. The solution forms, we have the same type of equation, but you notice there's another term in here now, that Cx term, or Cx dot. It's the dampening factor times the velocity is included in these forms now. So you see the forced vibration and the free vibration terms have those dampening terms in there. And we can still write that in terms of a magnitude times e to the st power. But now there's just more possible solutions for s instead of just being imaginary. The imaginary one was that there was no dampening. If it's a complex number, then there's a damped free vibration, which is like the picture shown here. And you see that there's a oscillation plus there is a exponential decay going on. And the third possible characteristic of S could be just a real negative value, and that's when you only have exponential decay, when there's no no oscillations going on at the same time. So a little bit about dampening, and we'll be talking about that a little bit later. So right now we're going to focus on how do you find the natural frequency of this system. We're going to look at two methods today. The first one is when you write out the equation of motion, which is some of the forces is ma, or some of the moments is I alpha. We can rearrange the terms in there in order to get the natural frequency. And the second method, the other example I'll show you, is just assuming that you know the mass of the system and that you can find the stiffness of the system due to some type of load. We can calculate how the deflection will occur. We can find the stiffness by taking the load and dividing it by the displacement that it causes. Or we could take a moment and divide it by the angle of twist that it causes. And then we can use that to directly calculate the natural frequency. So those are the two examples I'll show you. And I'll give you a little activity on that you can use with the second method. You can probably use it for either method, but that's about all we have for now. Watch the examples, and there's a little angel activity to work on after that. And when you come back from break, we'll continue on with finding some natural frequencies using some different methods. And don't forget, your project is due after break. So I will see you then, and enjoy your time off.